So here are some introductions to the ideas that we're going to be using in Unit 3 and Unit 4 for dynamics. Well, we've talked about acceleration and what happens when an object accelerates, but we haven't talked about what causes something to accelerate. So this really became important as people were starting to understand how objects interacted and how objects would actually change their motion. And Isaac Newton really kind of pulled a few ideas together. And one of the first things he did was use Galileo's definition of inertia, which is that the idea that an object that's moving in uniform motion, meaning a constant velocity, straight line motion at a constant speed, stay in that motion unless acted on by an unbalanced force. That means it doesn't mean there are no forces acting on it. It means the only time it changes its state of motion, the only time it accelerates, is if there is an unbalanced force. The force in one direction is greater than the force in the opposite direction. So you need something to cause acceleration. Things don't accelerate on their own. And the way we measure how much things resist the acceleration is their mass. The more mass something has, the more what we call inertia it has. So this is basically how objects change how they accelerate. That's why it's easier to push an empty basket than it is a full basket, because it has more mass, more resistance to acceleration. Newton's second law just quantifies what this interaction is. Basically, you'll see this long, ridiculous version of it in the textbook. But basically, what Newton's second law means is to get an acceleration. An acceleration means a change in velocity, or the rate of change of velocity. It's a vector, it has direction. So it depends on all of the outside forces acting on the object. So the sum of the forces divided by its mass. So you add all the forces together, and we'll talk about how to do that in just a moment. And then force is measured in newtons. 1 Newton is a kilogram meter per second squared. Now, when you're looking at a problem, when you're looking at something to find acceleration, excuse me, what you have to do is draw a free body diagram. And what you include in a free body diagram is a dot to indicate the object that you're looking at. And we're not going to be looking at force diagrams where we're labeling exactly where forces interact. We're not looking at rotation yet. So all we care about right now is the actual forces that are on it. So you have a dot to indicate our object, all the forces that act on that object. So you draw those as arrows, showing which direction they are starting at the dot. Some people do free body diagrams where the arrows point toward the dot, and that's fine. I don't have any real problem with that, but that's not the way I learned it, and it makes it easier if we just learn one way of dealing with it before we start changing things up. And then you make sure that if any of the arrows are, any of the forces are a stronger force, the arrow needs to be longer. If it's a weaker force, it needs to be shorter. And that force, each force is an interaction between two objects. And we've talked about that before, but forces are an interaction between object A and object B, whatever object A and B are. There's always two objects involved. Like the weight of an object is the earth pulling down on it. The normal force is whatever table or floor or surface that it's touching. There isn't a normal force if it's hanging in the air. There isn't a normal force if it's being lifted by a string or is flying or something like that. There always has to be an interaction force. You don't just draw forces because you've used them before. And then once you've done that, what I want you to do is look at whether or not there's an acceleration. Now, you may not be able to complete the free body diagram with all the information at the beginning. You may have to go back and finish that later once you've solved for acceleration. The next one is Newton's third law, which is actually a fairly confusing idea. you usually see it written as for every action force, there's an equal but opposite reaction force. I don't like to think of it that way because we usually think of an action and then there's a delay and then there's a reaction. Like, somebody says something to you, so you punch them in the eye. That's not necessarily action and reaction. What we're talking about is the idea that every force is always an interaction between two objects. So if I'm touching the chair is touching me. So there's an interaction there. If I'm sitting in the chair, I'm pushing down on the chair because without the chair there, I would be falling to the floor. But because I'm not falling to the floor, I push against the chair. And so the reaction to that is the chair pushing on me. So it's usually opposite direction. So I push down on the chair pushes up on me. If I'm sitting there and the chair is balancing my weight, I'm pushing down with 220 pounds on the chair, and the chair is pushing up with 200 pounds on me. But they don't cancel out because they're actually on two different objects. Because one force is on object A, the other is on object B.